Assalamualaikum warahmatullahi wabarakatuh and good day. Let us now continue with our example of this balance three-phase topic. And then this following example says that a balanced 400 volt three-phase supply is connected across a balanced load of three impeders, each consisting of a 32 ohms resistance and a 24 ohm inductive reactance. So it consists of the R and also the real and imaginary value. So determine the current drawn from the power mains if the three impeders are Y connected. So using VRN as the reference phasor, so draw the phasor diagram. So this is how it looks like. You have the supply of 400 volt and the load are connected in Y configuration. And the first solution is to figure out the value of impedance Z. So where Z equal to R square plus XL square and square root everything here. So you just substitute the value of R given in the question, SL also given in the question. So you will get Z equal to 40 ohms. So this is according to this relationship. Okay. So we have the Z, so the magnitude. So we have this is the angle theta. So tangent of theta, this is equal to, so tangent of theta. Okay, trigonometry we have tangent of theta, this is equal to JXL over R. Okay, so according to this equations, you may get the value of theta, so the angle, which is arctan of XL over R. So you substitute again the value of XL as well as R, so you will get 36.87 degree. So following the four-phase load impedance, so ZRN, this is equal to ZYN because of the balance system. Okay, because to the balance system. So this is equal to Z with theta degree, so 40 as the substitution, so 36.87 for the angle. So magnitude of the phase voltage across each phase impedance is divided by, we have the VL divided by square root 3. So 400 over square root 3, so they give us 230.94 volt, right? So the phase line to neutral voltage are VRN equal to V phase. So remember, this is the reference, so reference always comes with 0 if not stated otherwise. So unless it's stated in the question that your reference with certain angle, then you should write here. But common or in common, if the question asks you to take VRN as your angle without any specific degree, so you should start with 0. Okay, and then the VYN, this is the phase with 100 minus 100 degree away. Again, substitute the value of magnitude, which is that we just calculated just now. So this is the angle, and then what you're expecting later on is VBN with plus 120 or minus 240. So it's the same location. Okay. Then therefore the phase load current IRN is, according to Ohm's law, we have V equal to IR. So rearrange the equation in terms of I, and then we get IRN over VRN, equal to VRN over ZRN. So again, substitute the value of VRN we just calculated just now, and then with the also the value of Z, so the impedance, so you may obtain 5.77 with the angle of minus 36.84 degree. So this is for the I. What happened to IYN? So you don't need to repeat the calculation, but we can simply use the information or the knowledge that IYN lags behind IRN by 120 and IBN leads by IRN by 120. This is according to the phasor diagram of a star configuration. So we have over here the this is for example the RN. Okay, so we have next is actually the YN as well as the SDBN. Okay. So they are 120-degree difference or 120-degree apart from each other. So by having said that, so we have yin, this is minus 120, so minus another 36.87 taken from this value, right? So we got 5.771 with a new angle of theta. Okay. Similarly, for IBN, so we have the same magnitude, but with now we have plus 120, so minus 36.87, you got a new value of theta or angle. So plotting the phasor diagram, so IRN, the phase, so YBN, the phase current, this one, our IBN phase current is drawn in red line or in the red arrow. So basically we have RRN, which is lagging behind VRN by 36.87. This is consistent for all of these type of phase. The second phase as well, and the third phase as well. So they are all differentiated by 36.87 degree lag, okay, or lagging. So the next example, 4-wire 3-phase supply is connected to a balanced 3-phase load. So the connection being 3 phases plus a neutral conductor. So again, so we have the 3-phase neutral conductor with neutral means it is star connection. All right. So if VRN 240 volt, 0 degree, and the impedance ZL equal to 10 with 30 degrees, and then the phase sequence is RYB, positive recurrent sequence, then find IR, IY, IB, and IN. So IN is the neutral current, the current in the neutral. So just imagine we have the flow of the IR is going downward or heading to the neutral point. So we have the neutral point over here. So the same thing for Y phase. So we have another Y over here. This is IY coming to the end point, as well as the IB coming to the center point, which is neutral wire. So we have, okay, this one is IB. So, and then this is to show you the direction, the magnitude, as well as the direction of the current flow. So this is the flow, the direction of IN. All right. So simply say that according to KCL, so you can see the total of I. And this is equal to I R, okay, plus by IR plus IB. Okay. Sorry, I should use capital Y over here. Okay. All right, then solution. So Ri, so take the value of VRN, given an equation. Again, the LL also given, provided an equation. So this gives you 24 negative 30 degrees. So you can expect that the rest of the phase IY and IB, so all the angle are shifted by minus 30 degree. Okay. So using the fact that phasor IY lags by behind IR by 120 degree and phasor IB lags IR by 220 degree, we can straightaway write so this way. So you have initially the minus 120 in for IY and then minus 240 for IB. So you just add up with negative 30 for IY as well as IB. So simply like that. Okay, so as simple as that. So IY now having a new angle as well as IB. Okay, so this is a similar, is either minus 270, is either 200 and minus 220 from reference over here. This is actually 200 minus 220, just to get your idea better or clearer picture. So you can also say that this is from, this is also actually 90 degree for the upward direction. So this is 90 degree. So the same thing actually. And then if the neutral current direction is drawn outward from end node, so the Kirchhoff, so this is what I mentioned earlier. So you have seen that according to KCL, so you are able to come up with this relationship. So we apply here. So now we apply here. So we can actually got the summation of IN, or calculate the summation of IN and give you 0 angle. So this is what we have mentioned earlier in this study, in this class, that for the balance system, so you may get that the value of In is equal to 0 because they are all balanced or equal. And then the phasor diagrams looks like this. So we have VRN, so we have IR which is lag by 30 degree. So similarly for IY, which is lagging 30 degree compared to VIYB as well as BR. Okay. So another exercise, so a star connected three-phase load has a 6 ohm resistance and an 8 ohm inductive reactance. Again, so we have the R value and also the I value. So the imaginary value as well as the real value. So in terms of inductive reactance, so it is connected to a 415 volt 4-wire three-phase supply. So 4-wire means we have 3 live. Okay, and then the plus one neutral. So write the phasor expressions for voltage across each branch for line voltage and for line currents when the phase current is RYB, so the positive sequence, and also RBY, the negative sequence. So this is how the diagram looks like. So we have the 415 for each line to line value. Okay, it's at the RY, it's at the RY, 415. It can be also 1Y at YB, 415, or as well as R and B. Okay. So it's connected in star connection or star configuration with neutral wire. So, okay, this is going to be your exercise. All right. So I will make it as one of your assessment. Okay. So let's look at the another sub nodes where delta load current and line current relations. So line currents in the delta connected load RY and IB are connected to the corresponding delta load currents IRY, IYB, IBR according to Kirchhoff current law. So you can simply that, so looking at the direction of IR, this is actually equal to, okay, this is the direction of IR. So going to node R for over here, for example. Okay, so we have coming IY, IBR. Okay, so you need to deduct that. So you need to minus that, and then we have here RYB, RY, sorry, so which is coming out of R. Okay, this is RY, so it's written over here actually. So we having said that, so we can simply write down that IR is equal to IRY minus IB. So R equal to IRY minus IBR. So IY equal to I again, you can apply at this node, for example. Okay, so just reapply the same concept. So the same idea on this node. So we have IY, so this is equal to IYB minus IRY. And the third equation implies that IB. So given a balanced three-phase system, the current flowing into data connected load can be defined by IRY, again, so the reference, IYB, minus 120 degree. So IBR, this is equal to 120 degree. So why we are interested to analyze on this all I's, so this all I's, okay, why? Because the phase of line voltage, okay, the phase of line voltage is actually equal to V phase, or yes. So there is no point to make analysis if the phase are equal between line, the voltage are equal between line voltage and phase voltage. So that's why we are interested to know what happened in IR, IY, and IBR, since they are all different from one to another. Okay, so again, similarly to what we have seen earlier, so they are actually 120 degree apart. Okay, so 120 degree, 120 degree, and 120 degree, but this time in terms of I. Okay, Y, RI, RY, IB. And then phasor diagram in data connection, the line current lags the phase behind phase current by 30 degree. So this is minus 30 degree. And what happened to the lines current? So you have to multiply by square root 3. okay, times the magnitude. So therefore, we can simply write in terms of mathematical equation. So IR is actually minus, okay, this is the line current. So this is the phase current, okay, I phase. So IR equal to square root 3, I phase, so minus 30 degree. So this is IR. So this is the line voltage, the line current, sorry. So this is the phase current. So it is lagging behind by minus 30 degree. Okay. So for IY, similarly, so this is for the IY. So if you compare to YB, the phase current, so this is another minus 30 degree. Okay. As well as, but if you try to plot it from IRY, so this is actually 150 degree apart. So IB, so minus 270 degree is over here. Later on we'll see, so this is how it looks like. So IB, so this is minus 270 from IRY, okay. So example, 400 volt 3-phase supply is connected across a balanced load of 3 impedance, each consisting of 32 ohms resistance and 24 inductive reactance. The I, again, this is the R, and so this is the I value. So determine the currents drawn from the power mains if the 3 impedances are connected. So we have a solution over here, complex load impedance with ZL equal to R plus JX. So we have the 32 plus J 24 ohms. So therefore, magnitude of load impedance is, or the modulus of ZL, so we have square root R square plus X square. So substitute values, you may get the value of ZL, which is 40 ohms. All right. So what happened for the phase and line and phase for voltage in this particular example? So data connected load is having V phase equal to V line with the same value of V, which is 400. So therefore, phase current, so you need to convert the value. So you have to have the new calculation over here where the IVH equal to V over ZL. So this is according to Ohm's law, V equal to IR, right? So 440, okay, this is giving you 10 ohms. So for data connected load, so remember for line, so you have to multiply with phase, right? So this is the V phase, so the magnitude of the impedance also in phase, so you have to standardize everything into phase. So it's no problem, we come to the voltage because V phase is equal to V line, even though the question, the voltage of the question, voltage of the system is given in line, okay, in this particular example. So 400 volt, so it's actually V line and V phase. So having said that, we have V phase over here over the phase impedance, so you may get the value of I phase. But when come to load, come to the line, so you have to be careful, multiply by square root 3, and this gives you 17.32 ampere. So and the exercise for you to go through, so this is the answer. So I will pick some of the exercise as for your another assessment. So another exercise with the data to the star data connection or star data configuration. So this is the answer. And then another good exercise for you to have a better understanding of this particular topic. So summary. So thank you very much for your time. So we'll see in the next coming chapter on the unbalanced